right?
Yes.
Okay, so I today want to talk about large language models, and as for this knowledge event, I actually do not want to talk too much about the projects what we're doing with large language models, but more about the technologies or technology of LLMs itself. So what it is, how it works, because I think it is more important to actually know what is the technology behind it than to me just talk about our projects, what we're doing with it. Of course, we can discuss the projects maybe later, but today is more about maybe less radiotherapeutic specific, but more general large language models. So what are large language models, or LLMs? So I think many people, when they hear of LLMs, they think about ChatGPT. They think this is like some kind of magic AI system, some computer that can talk and understand and just like a human. And there is some sort of magic behind it. And even though the technology certainly is very, very impressive, and it like the potential to use it for all kind of applications is really immense, it is not a magic thing. And it's like, therefore, I think it's also important to understand how this technology actually is working. Now, let's say we want to build a large language model. I think this is a good approach to show how the technology works. Like, what do we need to do? So step one, we actually first need to get a lot of data and prepare it for training. So of course, it is language, it is text. So we need a lot of text data. And therefore, like, you basically take the text data from the internet. Now, you just don't take it like that, but you want to probably filter your text data. You want to do some URL filtering, that you don't have like all kind of websites, but only, or you exclude websites that are not relevant for your purpose. You want to extract the text from your web pages, because as you know, like most of the internet is not just plain text, but it's HTML code or some sort of computer code. And of course, what is relevant for us if we want to train a large language model is primarily the text itself. Then you maybe also want to do some language filtering if you're like specifically interested to train a model in English language or whatever language, and so on and so on. So you can really like filter the text data that you want to use for your large language model. But in the end, you really need huge amounts of text data to train a model that is performant. You also want to duplicate the text data that you have, so you don't have like multiple entries. And typically what's also done is like the removal of personal identifiable information, like some personal IDs, names, and so of information. So there's a lot of filtering going on before you actually have the data that you want for training. Now, to have a look what this actually looks like, I want to switch to this browser. Like, one example of such text data that can be used for training of large language model is this FineWeb data set. Now, this is exactly that. Like, it's like data from the internet, all kind of text data that has gone through all these filtering steps and pre-processing steps. Here's everything described how this was done. And basically, this kind of data is freely available. And anyone can use it and download it. So this is 51 terabytes. It's really a lot of data. Now, okay, so we have our data prepared. Now, to use this to train a large language model, we need to turn this text actually into numbers, and this is the process of tokenization. Now, let's say we have text, but what the computer is a one-dimensional sequence of symbols. Now, of course, if we have some text, like for example, here, this text is actually the Wikipedia article of radiation therapy. You can see, of course, this is a one-dimensional sequence of symbols as natural language as we know it, but this is not what is ideal for the computer. For computation and also for training the model. Of course, what the computer actually sees is not our natural language, but is, if we go from this, it sees everything as bits. So it's ones and zeros. which are grouped into bytes. So, for example, first 8 bytes here are, in this situation, would be the letter R that you see here. And so you have all these bytes, which is the same information as here, but just as bytes instead of letters. Now, this is a lot of text, or a lot of, it's a very long sequence. And this is not ideal if you want to train a model. Like, what you want to have is actually this one-dimensional sequence of symbols that is not too long, so that the computation becomes efficient. Now, what you do is that you reduce the length of this sequence by increasing the number of symbols that are available. Now, we have these bytes. So these are 256 different bytes with 2 to the times 8. So this way. But now, if you have all these bytes, so this is the same as this. It's just with numbers instead of these blocks of 8 bits. And now, what you can do is that you reduce these number of symbols by basically merging patterns that are very frequent. Like, for example, if you let's say, for example, this 6420. If you search for this 6420, you see this is a very common sequence. It occurs a lot. So it makes sense to just not write 6420, but to replace this with, let's say, a new symbol, which would be number 257. And thereby we reduced overall the length of our document and increased the number of our symbols. This is done again and again. And normally, or what is usually done, that you end up with about 100,000 symbols. This is a lot of symbols. And these are basically all just these tokens represented with numbers here. And so this is the same text as we have here, or as we have here, but you can see it is way shorter because we have so many symbols that, like, basically are able to present like multiple letters or multiple bytes actually. Then we can drastically reduce the length of our text. And this is basically what's done with tokenization. Now, if you want to have a look how this actually looks like. Now, this is a tool called TechTokenizer. Let's say we go to our Wikipedia article of radiation therapy. You can basically put any text in there. And now let's say we have a large language model like this GPT-4o. Now, this is actually what the large language model is using for its computation, or what it sees. Like, you see, these are these numbers representing all these tokens, or here also in color coding, like, for example, this RADI is one token and this ATION is another token. And this is like basically this text of the sequence of tokens. So this is what a model sees, and this is what we as humans see. All right. Now, we do this to make the computation more efficient, because now in step 3, we're actually going to train a neural network, which is fundamental to the functionality of a large language model. Now, let's say we have a token sequence, or a like for us it's like this text, but for the model it's like these tokens, these symbols. And basically what an LLM does is that it predicts how a given token sequence or a given text for us would continue. And this is basically done by a neural network. Like, you get it as an input, this token sequence. And then basically the output is for all your, let's say, 100,000 possible next tokens that can occur, the neural network will predict the probability for the occurrence of each based on this sequence. Now, in the beginning, of course, you don't have any probability, so the probability will be equally distributed or randomly distributed. So in the beginning, let's say we have like 100,000 possible tokens, a probability for each of 0.001. And now what we do is, in training, we actually use our data and present the model sequences of token sequences from 0 to several thousand tokenses. And then basically ask the model what is the next token. So we give the model our sequence, and basically, let's say we have here our sequence of tokens, and when really during training, like maybe you give this sequence and you are basically, then it should predict the next token, or you give this sequence and then it should predict the next token, and then it takes the next sequence and should predict the next token, so on and so on. Let's say we have this sequence, and when we know in our data the next is radiation therapy is a treatment, which is actually has an own token for itself. And now, based on that, you can update your probabilities so that this token with number 7448, or this symbol, basically increases the probability, let's say, to 0.002%. And of course, all the others decrease. So you adapt this. And of course, you don't train just once, but you repeat and repeat and repeat. And after a very long time, you end up with a model that is actually quite good in making these predictions. So if you give it a token sequence like that, like radiation therapy is there, then like it will give you a probability for each of the possible next tokens, and it is much more likely that the next token will be treatment than like some random token that doesn't make any sense. This is basically how an LLM works. Now, how does this now look like? So if we go to, like, this is an interface where we can basically start this. Let's give it just some part of text. And when we put this in, and you will see that the LLM will just continue with some tokens. And you see in this case, it made some weird list or something. And of course, you can do whatever text, and basically it will continue to predict how this will continue. Now, this is actually already quite useful for some use cases, but this is not what you actually want, and this is also not what ChatGPT or something is, because let's say we ask it a question, whether today, or okay, what is, I don't know, what is the capital of France? It can actually, sometimes it answers that, but sometimes it also does this, you know, it just predicts how this can continue. And based on the training data, it can also like ask some other stuff. And this is not very useful. This is not what we would want in most use cases. We actually would maybe want a useful assistant where we can give it a question and then it gives us an answer and not just some continuation of our token sequence. So what we do next for step 4 is therefore we take this model and further train it and adapt it to create an assistance system. And this is basically what you do with this supervised fine-tuning. It's basically when you have this base model, like this is a base model, this one, when you train it to give do additional training based on specific data set that you give. And what we would want for an assistance system is that we have questions and then it answers to these questions, gives helpful answers to that. And to do that, we of course need more data, and we need specific data of a helpful assistant. Now this data would probably be a lot of conversations. Like let's say, for example, we have a question, so what is radiation therapy? And then the answer is radiation therapy is whatever, like something that is useful to that. And you may have another question like, why is the sky blue? And it gives an explanation to that, and so on and so on. And you have like a lot of it is faced with such questions. Now this, in the development of the first useful LLMs that did this approach, like this was actually done with specific data set that was manually created by professionals who were like actually tasked to create these kind of conversations and give very useful answers to this kind of questions, like to have questions that give useful answers, so that you have a large text corpus that you can then use for this fine-tuning. Now, however, that is not everything, because if we give just that, like the model does not understand what is what is the user asking or whatnot. As we saw before in this example, it can like also be just some text sequence, like some book in which where is a question written, but it's not a agent, not a user asking an assistant or something like that. So to do that, what is being used is that LLMs now use these additional special tokens. Like this is an example for, I think it's a Llama series that uses this kind of text or this kind of text string for defining these tokens. Basically, you don't train the models on this kind of text, but you put this text within these additional texts, which are additional tokens, so that the model can understand. And everything in between this is what basically the user is asking, and everything afterwards is what the assistant is asking. There's also this system prompt that can be used so that you can use to basically assign a role to the model, like you are a helpful assistant, or I don't know, you're a system for classification or whatever you want. So these are additional tokens that have been created for this purpose, to get from this base model that is just predicting how a token sequence is likely to continue, to this kind of more specific assistant system. Now, when you go to ChatGPT or some other system, some other chatbot system, what you type in here, what is radiation therapy, is actually in the background, there is this kind of additional text sequence, or part of this token sequence is added automatically, but you don't see it as a user. There is some sort of system prompt in there telling the model how to behave. And also this is inserted, then comes a question, and as soon as you press enter or send your query, then also this gets added, and then actually until here, and then this token sequence is calculated how it should continue, so that this is really the answer of this assistant. Now you can do supervised fine-tuning not only for these use cases, to come from a base model to an instruction fine-tuned model, or to this assistant model, but to all kind of specific use cases or domains that you're interested in. There's actually also one large language model that had been, or maybe even several LLMs that had been fine-tuned for radiation therapy. Now this is a bit outdated. This is has been the Llama 2 model, which is not anymore state of the art, like not even close. But basically, there are all these kinds of specialized models, LLMs, to specific domains or use cases. Now, there are a lot of problems still, even if you have this assistant system, and probably all of you have used ChatGPT or similar chatbot interfaces using LLMs. These are very useful systems, but they have some considerable problems. Most importantly, probably is the issue of hallucinations. Now, what hallucinations means is basically the problem that LLMs can give you, if you understand that this system is just predicting how a token sequence or a text is likely to continue, there is no limitation, no fundamental limitation from the LLM creating some text that doesn't make any sense. Like, this is just likely how it is likely to continue, but it doesn't mean that this actually is true, what is now from a semantic point of view actually written in there. Now I can show you a little example on this. Now this is now Mistral 7P Instruct. This is another LLM, and this is actually this instruction fine-tuned model that really has this feature of this system. You see, I can also put in a system prompt, and I can ask it like questions what I'm interested in. I don't know, what is the capital of France? I mean, it will probably tell me Paris is the capital of France. And it will also, like if I put in some nonsense, it should, let's say, what is, without any question, it should actually tell me something that this is not I don't understand the question or something like that. Yeah, exactly. And it doesn't just continue what is and continue some text sequence that is more or less likely to happen in any given text from the internet. However, now the issue of hallucination is like you can ask it a lot of questions now, like for example, who is Albert Einstein, and is like the model will know who Albert Einstein is, so it will give you a correct answer to that, even though I actually had a spelling error here. It correctly identifies it was a theoretical physicist and so on. Of course, because there's a very famous person, and it's a lot of text about Albert Einstein was used in the training of the model. Now, so this works fine, and this is probably correct information. But if I now ask it, let's say, who is Oswald Gallagher? Now this is a completely made-up name, so this person does not exist, or at least is not some famous person that the model should know. And if I ask it, it will nevertheless tell me that, I don't know, it is a fictional character from whatever. If I do it again, it will tell me something else. Was an American author, an entrepreneur, or was an artist. So basically, the model like tells you, like has been trained on a lot of these things, but of course it hasn't been trained on who is this specific person, and then it will just make up things because it's like not unlikely that this text sequence is likely to continue like this. Now, this is of course a problem. You can also do some other examples. For example, you can ask how many are in strawberry. This is a famous example. And this is, okay, what did I do there? Okay, it didn't understand the question actually. It's how many are in strawberry? Approximately 0.5 are the average strawberry. So this doesn't make any sense. Or like let's try again, regenerate. Okay, it makes up some numbers, but it doesn't understand that that the letter R is actually meant in strawberry. But even if it did understand, it would not would have trouble to correctly identify it. And it's actually not surprising that it doesn't know that, because if you put strawberry in here, the model doesn't see the letter R. The model sees like 3 numbers or 3 symbols that represent some text, but it doesn't understand that there is no understanding to it. It's just like a continuation of this token sequence. All right. And one other example, I think I had here, how many dots are these? And let's just, so these are 5 dots. Let's just make, so this should be 50 dots. And it tells it's 26. And if you ask it again, it's 26 is 10. It's 26 again, it's 9. So this doesn't work, obviously. And the problem is again like that this model is like if you put in these dots, it just sees like some numbers, but doesn't have an understanding. It cannot count these dots, because really the LLM fundamentally different, like interprets what the text or token sequence than when we as humans do, and it is just predicting how this token sequence here with the system prompt, here with the user prompt, here with the assistant prompt is likely to continue. So now what can we do against these problems? Now, these issues have not been fully overcome, but there are several ways, and also quite successful ways actually now, to mitigate these hallucinations. You can actually train the model to answer with the answer "I don't know" in situations where it does not know the answer. Now, we cannot, of course, have a complete set of all kind of possible names where the model then should answer "I don't know" this answer. But how this actually works is that you have 2 LLMs, one LLM asking the model questions where the answer is no, and the actual model that is being trained like answers this question, and if the answer that the model gives is not correct over like several times, then the correct answer is actually not some arbitrary value, but the correct answer is I don't know this answer, and then you can create this data set that you can fine-tune the model on so that you can mitigate this problem a bit. Another very useful approach is actually using tools. Now, what you and I would do if I asked you who is this person that you have never heard of, you would probably go on the internet and search for this person and find out what you can. And we can do the same, also use the same approach for the LLMs and let it use web search tools, calculators, or also code interpreters and all kind of tools. This is actually sounds tricky or complicated, but it's actually not, because you actually do the same thing. You have your token sequence, and as we had before with these special tokens to identify what is the user saying, or the special token, what is the system saying, and so on, you just add a new special token like these search start, where the model then creates this token search start, puts in the query, and this basically triggers this tool, which is not the LLM itself, but it's just a software which then will put this into a search engine, and all the text that the search engine gets put into this context window, into this token sequence, and then afterwards the assistant actually answers. And when you have all this token sequence of all this information about this person, like about this George or Oswald Gallagher or whatever, in your token sequence, and then the LLM predicts how this is continue, but it knows or has all the information from a web search in its own context window. All right. And the same you can do with calculators or code interpreters or whatever. And this is basically, if you go to some ChatGPT or whatever, if you put this search or suche, if you click on it, then it will do exactly that, but it will do an internet search. Now, next step is revenue, and this is actually, I think, where things really get interesting. I mean, these are very helpful systems already if you are able to mitigate these hallucinations. But now all the problems where we've looked on so far is basically this crafted solution where you have a question, like you ask the model, like, what is the capital of France? And it will tell you the capital is Paris or whatever. And you have to craft all these dialogues so that the model is basically just more or less copying what you are telling it, or the data that you give it is just copying. And this is fine, but you can also do this reinforcement learning, which is basically using the model to find solutions by itself. Now, what you do here is, let's say we have this question. So Anna is twice the age of Ben. 2 years ago, Anna was 3 times the age of Ben. How old are they? And you see Anna is 8 and Ben is 4. This is the correct answer to this. And now what you can do, let's go back to our Mistral model. Now what you can do is that you give this, actually, let me briefly copy this. You can give this to the model. This system prompt. So here, you can give this to the model, and it will come up with some solution. And this, what it came up with up here, is actually, in this case, not correct. You see Anna is 8, Ben is 4. And it came up with a solution like Ben is 1 year and Anna is 2 years. And this is not correct, obviously. Now we can, of course, try it again. And now it's 12 and 6 years. And we have another 24 and 12. And it actually tries to reason it and find some solution. And let's find actually some, like there is, of course, a chance that it actually gets it right. Here. Anna is currently 8 and Ben is currently 4. And you see the model, like actually in one of these situations, I actually gave the correct answer. Now you can repeat this again and again. And in some cases, the token sequences that the LLM will produce will lead to a correct result, while in other cases it won't. Now, we didn't tell the model that it should like do these calculations and this is the answer, but the model actually was in some cases gave the correct answers based on the token sequences it produced itself, and in some cases it didn't. Now we can use that to train the model again. Let's say we have these token sequences and we see in some of the situations the model actually get it right, and so this means that this kind of token sequence that the model produces is very good. However, in these other cases, something went wrong. Like in some cases, something in the creation of this token sequences was not correct. And so these are the better kind of token sequences, and we're interested in them. And we can train on them. So we use these successful token sequences for additional training. Of course, we don't use just 6 or 7 sequences and not just one problem, but we can automate it. So we have like thousands of problems and thousands of sequences, and we collect the ones where the LLM was getting to the right solution, and then can again train the model on that. And the interesting thing about this is really that the model does this basically on its own. Like we just know the answer and we know the question, but we don't tell the model how to get to this answer. And this is what probably you heard of with the DeepSeek paper and the DeepSeek model. Now, DeepSeek, they did not invent the concept of reinforcement learning, but they published this open source paper on it, and were kind of the first who really like showed in a paper how this can be done and should be done. And what you see here from this paper is basically that the models increase as you increase the training of this on these kind of data, and also that the token sequences, interestingly, get longer and longer, and basically the model creates these token sequences, and thereby, like on its own, whereby it actually tends to solve these kind of problems. Like it naturally learns to solve reasoning tasks with more thinking time. Now, it isn't thinking in a way that you and I think, but it's just this creation of token sequences that lead to correct results. And this is what you can also do with this, like with DeepSeek. Let's say you're here in DeepSeek, and now if you put this thinking button on, the same is also there for ChatGPT or other chatbot models. Let's ask it some question, like we can again just what is the capital of France? Now this is not, or let's what would be the capital of France if it wasn't Paris? Now this is a bit of a weird question, but basically what the model will do now is that it will like not think, but what you can see here is that it creates this first like these token sequences that are like basically created so that the model in the end reaches the correct solution. Now this is not a verifiable whatever solution, but basically it just thinks of that, and then this is what actually the user sees or should see if you turn this out, when it's like comes up with some sort of solution. And this is what reinforcement learning basically is. And this is very powerful because it's like working without human intervention. Like humans only give it the task and know the solution, and then the model trains on its own what are the correct solutions for that. Now, a quick word about multimodality. We so far have only talked about text, but in principle, all of this also goes for images, audio, video, 3D object, whatever. And the reason is basically because for computer, everything is just bits and bytes. You can represent all these just as token sequences that are not representing like letters in the text, but certain parts of this information. Now, this is basically more or less where the state of the art is now. But I also want to like briefly talk about what might come next, because I think this is very interesting, and it's very a fascinating time now. What is going on there, and all this technology has been evolving like over the past few years. Now, one thing that is likely to come, or what people think is coming, is that you will use these LLMs more and more as kind of independent agent systems so that they can more autonomously solve some tasks for you, like that they use computers or write computer code and so on, and like that they can act on their own more and more. However, what is, I think, even more interesting is this approach. This is a paper from Google DeepMind, maybe you've heard of it, is like this Alpha Evolve. Like this was published not even a month ago. And basically, this is about coding agents. And like, because computer code is also just language, is just token sequence. And these systems, these LLMs are particularly being used for coding, of course. And like, I mean, it's a technical domain, like state-of-the-art models are like directly for used for coding purposes. Now, there are these coding agents that can create computer code. And basically what this Alpha Evolve paper is about, that you combine this with an evolutionary framework to create these kind of coding agents using LLMs to solve certain algorithmic problems. And this is very interesting because it can really on its own find solutions where you don't even maybe know the answer, but you just kind of have some sort of evaluating it. Basically, the way it works, you have some sort of LLM, and you can have any LLM in there. And you have some framework where the LLM is then asked to solve a problem that is defined by the user and to write computer code to solve this problem. And this computer code is then executed and the performance is evaluated. And at the same time, you create these branches. Now, this is from another publication, but it follows a similar approach. You basically have your coding agent that can write computer code. And then you slightly change this coding agent so that it will create other code and again evaluate it, create code, and then again branch off. And you have these evolutionary trees where you have all these coding agents. And you see in the first coding agent doesn't solve any problem. Like I said, 200 different tasks. But in the next generation, you have few agents that actually can solve something, then the next some more and so on. And after a few iterations, you get some very good coding agents that can solve a lot of these problems. And this is basically also what they did in this Alpha Evolve paper. And why is this so interesting? Like, this is from the paper, they are actually able to solve several or use this on several mathematical and IT problems, and was actually be able to outperform the current state of the art in several problems. Like, this is just examples of state of the art breaking mathematical constructions discovered by Alpha Evolve. And these are very complex problems that people have been working on for years and years. And these are also like computer problems that themselves are being used by the AI. And why is this so interesting is because you can basically, with this kind of approach, it might be able to create AI systems that improve themselves and can create better code and again improve AI and so on. This is what basically this theory of this intelligence explosion is about, where you have like automated AI research that can on its own figure out new solutions to problems. And so this is very new, and I think it's very interesting because this is really where a lot of things are going now, and it might really be very interesting to see where this will lead us, and so that AI can really solve a lot of problems that have not been solved and outperform current state of the art. Sorry, can you hear me? I think my microphone just had a problem.
Yeah.
Okay, perfect. So just a brief word in the end about applications of LLMs in radiation oncology. As said, I wanted to talk a bit more about LLMs in general. Of course, we can use them for all kind of different tasks like data extraction, literature screening, classification tasks, summarization, answering clinical questions, administrative tasks, and so on and so on. So really a lot of tasks like that we specific problems where we have also in radiation oncology, we can use them. We have done a lot of research on this, and a lot of people are doing research on it because the technology truly has a lot of potential for useful applications. And this is also why I think it's important that we also talk about it, but because we have specific problems in radiation oncology that we want to have solved, where this technology can help us. And it is important that we participate in that, and we shouldn't wait for Google or Meta or whoever to come and solve our problems, because this is not going to happen. And we really need the clinical input and the expertise of knowing what are actually the problems that we want to have solved. And this is a powerful technology, but we should know how it works, like at least basically how it works. So we know how, like, what are also the limitations, the problems, and how we can best use it. And that's basically it. Like, thank you very much for your attention.